All right, so tonight we're going to dive a little deeper into neural networks, look more into how we can tune them, mess with the hyperparameters to try and get a better fit, and to prevent overfitting, which is a common thing that happens with neural networks. So to start, we're just going to kind of go through some different things we can change and talk about them. Some of the stuff we covered last week, but we're going to go into a little bit more depth tonight. So the first thing, optimizers, we kind of talked about those. It's basically the function that does the gradient descent work. So there's a few different options. The first is kind of just the most simple. It's SGD, which stands for stochastic gradient descent. This is basically just straight up gradient descent that you would use in regression. The learning rate's static, it doesn't change, you set it and it stays that way the whole time. Pretty basic, but can still do a good job in some cases. Usually though, you need an adaptive optimizer. So the next one's AdaGrad, which stands for adaptive gradients. It basically has a different learning rate for each feature, and the learning rates change over time. One problem with AdaGrad, though, is that the learning rates tend to drop to 0 really quickly, and that can be a problem. So to compensate for that, there's RMS prop, which stands for root mean square propagation. It's pretty much identical to AdaGrad, except it doesn't decrease the learning rates as much, so they don't drop immediately to 0 like they do in AdaGrad. I've seen RMS prop used quite a bit. You usually wouldn't pick AdaGrad over it, but there's always cases of people, using AdaGrad or some other obscure optimizer and having it do a good job. You just don't know. It kind of really depends on the data set. But the most common optimizer, of course, is ADAM, which stands for Adaptive Moment Estimation. And this basically is identical to the previous RMS prop and AdaGrad, except it also uses a history of the gradients in addition to what the RMS prop and AdaGrad do. So it really compensates for things. It's really adaptive. And this is almost always the best option. It converges really fast. And you can also set the initial learning rate. I think the default is like 0.001. But you can kind of mess with that a little bit. And speaking of learning rate, so it's kind of a trade-off. A larger learning rate, you'll train a lot quicker, but you'll usually end up in a local minimum instead of a global one. On the other hand, a small learning rate will mean that you'll train a lot more slowly, but your odds are increased of finding the true global minimum. So usually the default learning rate on an adaptive optimizer can work well because it will kind of adjust, but you can change the settings, you can change the initial value. Usually they fall between this 0.0001 and 0.01, and then incremented within that interval, either times 5 or times 10. Usually you'll want to start off with the default, and then if things aren't working, if it's too slow, or if you're basically plateauing too early, you can kind of tweak it either direction a little bit and kind of just test it out stepwise. So the next thing is batch size. We also talked about this a little bit, batch size and epoch. So basically batch size is how many samples get passed through and trained on each time. And then epoch is how many times the entire data set goes through the network. So a couple things on batch size. Like I said, it's the number of training samples in one iteration, and the weights are updated after all those samples in that batch go through the network. A larger batch size can take more time and takes more resources on your computer to converge, but it can find the global optima almost always. Basically, if you set the batch size to however many samples you have, you're guaranteed to find the best solution, but it'll take a lot of time, a lot of resources. Your computer might not be able to handle it, and it can also lead to overfitting. So on the other hand, smaller batch sizes can be faster, and they can kind of prevent overfitting and be able to generalize well to outside data. But there can be a lot of noise involved since they're trained on just a few samples at a time. Depending on what samples they get early, it can kind of affect their training and they can get stuck in local optima. So usually there's a sweet spot. You don't necessarily always want the largest batch size possible or the smallest. You kind of want somewhere in the middle. So 32 is a recommended starting place. You'll see this a lot, but you can try basically any value. And you do usually pick powers of 2. I was reading up, and this is actually because just the way your computer deals with memory, everything is in powers of 2. So it's better for your computer to just do it this way. So you can start with 32, kind of go up or down from there. You probably don't want to go over 512, depending on your computer. If you're running it on your CPU or GPU, you probably can't go above 512. So it kind of just depends. And then on the other hand, you really don't want to go down below 8. You don't want to do like a batch size of 1 or 2. You'll probably get not a nice fit on that. There'll be lots of noise in it. So yeah, that's batch size. Usually just start with 32, but definitely something you can mess around with.
So does that have to do with the input or the number of input or like the neurons on the first layer?
It kind of does. Because like I said, if you have, 1,000 samples, you could do a batch size of 1,000 so that every time it trains on all your data points, you would probably get a good fit there. It would find the global maximum, but it will take a lot more time and more of your memory to do that. So it really doesn't depend too much on how many samples you have unless you have a small number of samples. If you only had 100 samples or something, then you probably could just do a batch size of about 100 and just do them all in one go. But usually with neural networks, you're going to have at least 1,000 or more, probably a lot more samples. So you'll have to kind of pick a value within this range. Does that answer your question?
I was wondering, so if we choose a batch size of 8, but on the first layer we have 10 neurons, does it mean that is too small? The batch size?
I see. The number of inputs. No, so it doesn't have anything to do with that. It's more so just related to how many samples you have.
Okay.
Yeah, so your input size could be anything really, and that wouldn't affect the batch size. All right, so something else you can add to a neural network in the training process is noise. So this can basically be added to help prevent overfitting, and it makes your model more robust. It basically tweaks the values on your layers, so it could be your input layer. You'll see here, let's see. Is that on the next part? Oh, no, that's on the, okay. So the noise can just be added as a layer. This is just in the Keras documentation. So you can kind of pick different ones. Probably just the Gaussian noise is going to be the main one here. It mitigates overfitting. It can just be added as a layer basically after your input or as the input layer. So I think I have an example here where they show it with code. Yeah, so let's see. Down here. Okay, so this is without noise. So we're overfitted because our train and our test are really far off. And then here they add it as the input. So it adds a noise of 0.01, so a really small amount. It just kind of changes the values a bit. And that kind of helps improve the fit there. It makes it a little bit less overfitted, which it still is. So maybe you'd want to add more. So yeah, see, this one's a little bit better. They went up to 0.1. So that can be an option. Like I said, you'll run into overfitting a lot. I think we saw that in the MNIST data set we did. I think all the models were a little bit overfitted. So that's kind of one option. Another option is regularization. This is related to L1 and L2 regularization. Remember lasso and ridge. And this can be applied to the weights, the bias, or to the activation function. So there's 3 different regularizers within Keras you can choose from. It basically does what lasso and ridge did with coefficients in regression. It penalizes larger values in the weights or the biases. And that kind of helps to prevent overfitting as well. So here's the 3 different types of regularizers, and you basically add them in as a parameter within a layer in Keras. So we have a dense layer, we're going to give it a kernel regularizer, and also an activity regularizer. And the kernel is applied to the weights, and the activity is applied to the activation function. So that's another option. And then a third one is dropout. This one's definitely really common. You'll see this a lot once we get to convolutional neural networks and doing computer vision stuff. So dropout works by basically randomly choosing a percentage of the neurons at any given layer and basically ignoring them for that training iteration. So if the network is relying heavily on one single feature to kind of predict and pass through to the next layer, dropout could basically disable that neuron for a pass, and then the network will have to rely on the other neurons, the other features, to try and make its best guess into the next layer. I had a picture that kind of had this make more sense, but it basically is just random. Like you choose a percentage, like 1 to 5% or something, and you can put it on any layer. You usually want it like after kind of like a larger dense layer maybe. And it'll basically choose at random each batch and disable however many neurons, and then it will only train the ones that weren't disabled and will only use their inputs to feed into the next layer. So those are kind of 3 different ways to help prevent overfitting. You could start with any of them. You probably don't need all 3. You could probably start with one, like dropout, see if that improves anything. And all of them you can kind of crank up how much they're doing. So like dropout, you can change. Let me see if I can find it here. I think it's core layers and then, yeah, dropout. So you can pass in the rate. So just between 0 and 1, it's the fraction of the units that will be dropped. You can also pass in a seed value to it. So it's the same every time. But yeah, so that's flat out or dropout. And let's see what's next. Early stopping. Okay, so this was something that came up last week too. You saw that sometimes it seemed like there was a point we should stop training because things kind of plateau off or training and tests kind of diverge. So a way to make it stop on its own is to implement early stopping within Keras. So it prevents a network from overtraining because you don't always know how many epochs you're going to need. So this kind of allows you to set a high value and then just let it stop once it notices the values are kind of leveling off. I think, okay, so this will basically make a data set here. It will do a train test split, and then it's just going to be a really shallow network. It's just 500 neurons on the input on the first dense layer. The input dimensions are 2. We only have 2 features. And then our target is 1. So it's a binary classification. And then it's basically just going to fit that model using the test data as the validation data. And then it's going to set it for 2,000 epochs, which is definitely going to be too many. And then we're just going to go ahead and check the accuracy of both the train and the test and plot it so we can see what happens. So go ahead and run this. I'll probably have to back out because the output will be really long. And we'll just wait a minute. It's a small data set, so it goes pretty quickly. Alrighty, so we got a training accuracy of 100%, which should always be a red flag, and then a test of 92.9, which is pretty good. We are overfitted, not terribly, but we definitely probably should have stopped training sooner. And it looks like the plot did not show. So let me just do this. There we go. So we can see our training. This is our loss. I guess that works. So this is the loss. So our training kept going down, our test was going down, and then we started overtraining, and our test loss actually went up then. So that's bad. So we should have stopped probably somewhere around here before our test loss started to increase, and basically where the training kind of started to plateau. So to do that, we have to import early stopping. All this stuff up here is the same. It's the same architecture as the first example. This is where we create the early stopping object. You pass in what you want to monitor. So in this case, we're concerned with our validation data or test data and the loss on that. And we want to minimize it. So that's what we put in for the mode. And then verbose will just basically make it spit out what it's doing. And then we'll go ahead and fit the model like before and plot it and see what the difference is. And again, we're doing 2000 epochs, but you'll see that it should stop. It stopped after about 240. And if you look up here, it kind of stopped, somewhere down here maybe. Basically, when it noticed that the test loss was starting to level off or plateau. But you'll notice our train accuracy is 0.967, and then test is 0.829. So that's not really great. I mean, we got better test accuracy on the overfitted one. So what we can do is actually add this other parameter into the early stopping called patience. So without patience, it'll basically stop it as soon as it notices a plateau. With patience, it will wait that many epochs to make sure that it's actually in a plateau. So once it notices that, oh, it's starting to plateau, it'll be like, okay, now I'll wait 200 epochs, and if I'm still at a plateau, then I'll stop. So we'll see what happens then if we run it again. You can see it's going for a little bit longer. All right, so now we went for 989 epochs, and we can see our graph here. It's definitely better than the beginning. And then we can look at our accuracy. So our test improved from the first example and also that second one we did without the patience. So
Matt, can you explain patience again? Is that the threshold? You were saying like it would run till 200 epochs, or it's like after the plateau run 200 epochs?
Yeah, the way I understand it is it'll notice it's at a plateau, and then it'll start counting. And if it goes for 200 epochs without the whatever we're monitoring decreasing, then it will finally stop. But if within that 200 window, it notices that whatever we're monitoring decreases, then it'll reset that basically. And so next time it plateaus, it'll again watch for 200 before stopping. Because sometimes when you're training, it might kind of, flatten off for a little bit. Like this is where it stopped initially, but you can see that there was more improvement to be made further on. Does that make sense?
So the first plateau we have is about 140, right?
Or about like 200, like looking at the orange line. Yeah, so basically it got here. It was like, oh, we're starting to flatten off, so I better stop. That was without patience. But with patients, it was like, okay, we're starting to flatten off, so I'll wait about 200. And you
Oh,
can
so
see right
after the
as it
plateau.
gets to, yep, so you can see right as it gets to 400, it starts to decrease again. So then it's like, okay, we're actually still going down, so I'll stop,
I see.
waiting. And then eventually it gets down, it started to go back up here. Probably around 800, it picked it up again. And then we can see it started to increase for 200. So that's when the patients like ended basically. So really to make this better, it probably should stop at 800.
Yeah.
So we could probably change this to like 100 maybe.
So like every plateau, it will wait 100
Mm-hmm.
until stopping. Okay.
Okay, so that was a little, wait, it was, yeah, 887. So that's a little bit better. So that's kind of just a value you have to play around with. But if you're training something for the first time and you have no idea how many epochs, you can just throw on a really big number here and then have your early stopping just so it doesn't go on forever and it'll stop once it's not improving anymore. And
And
then from
another
your graphs, you
question.
can kind of fine tune. Yep.
Oh, sorry. The other question I have is, I know you mentioned the loss of train task. Can you um, explain more? What is this lost?
So that's like on our loss function. So here where we compile, we're using binary cross entropy. So that's basically for binary classification. It's kind of basically a measure of, well, it's what we use for our gradient descent. It's what we're trying to basically optimize. So you can use that, or we could also probably use accuracy here. Yeah, so with accuracy, it actually stops a lot earlier. So you usually want to do the loss if you're monitoring something, because then the accuracy is just your metric that you check kind of afterwards. But for training, you're more focused on the loss.
Does it mean that my loss function is very low?
Yeah, so that's why we set like the mode equals min, because we want the loss to be really low.
Okay, okay.
Oh, aren't we still overfitted at this point though?
Yeah, we still are. But the early stopping doesn't really do much to help the overfitting. It just kind of makes sure we don't overtrain.
Okay.
So there's kind of a difference, like overfitting, overtraining. For the overfitting, we would want to do either the noise regularization or dropout.
Okay. That makes sense.
Yep. But yeah, if you ever see your graph and like one of the losses or accuracies starting to increase, that's a big red flag. So yeah, you'll definitely use this almost always if you don't know how many epochs to start with. Okay, and then one last thing before we get into the activity that's going to be important to know is how to save and load models. Because training takes a really long time for neural networks. You're not going to want to train something every time you open your notebook. And also to send a network to somebody else, to host it somewhere, you need a way to save it. So there's two ways with Keras. The first is to save the model structure, so like the layers, all that kind of stuff, separately, and then the weights in another file. So to do the model, you just call to.json off of your neural network model. This is the same as the one in the example we just did. And then you open a JSON file and write that model JSON to it. And then to save the weights, you just do model.saveWeights. You put in a name, and then the file extension is .h5 for weights. And then to load it from this method, you need model from JSON from keras.models. And you basically open the file, and then you run, let's see, and then you read the file and then close it. So you have your JSON, and then you pass your JSON into model from JSON, save that as your loaded model. And then off of your loaded model, you load your weights with this function here and just pass in the file name of the weights. And then one thing that's important is you still have to actually compile the model. So you still have to choose the loss and the optimizer and all that. So that will kind of load your model then wherever you left off. It will have the same weights and everything. You won't have the history attached, so you'll want to save that separately too. Which if you want to save that, you could save it like to a JSON file or a text file, or you could do like pickle. Pickle is a great way to save like a list or anything in Python. So you could do that if you wanted to save kind of the history of your training. But that's the first way, that's doing it separately. Because sometimes you want to use the same architecture as someone else, but you want to train it yourself, train it with different data, so on and so forth. So yeah, that's option one. Option two is to kind of do it together. This is a lot easier. You just call save off of the model. You save it as an H5 file type. And then to load it, you just need load model from keras.models. You pass in the file name, and again, you have to compile it. So that's saving and loading models in a nutshell. I'd recommend always saving basically your best model at any given time, like before you're about to close your notebook or something. Because once we get into capstones or just some of the labs even, training can take a long time. So you don't want to lose your progress. All right, does anyone have any questions before we go into the activity? Try some of these things out. Can I get a show of hands of how we're feeling about all this? Like thumbs up if you totally got it, sideways if okay, thumbs down if no. All right, so I saw some thumbs up and some thumbs sideways, so that's decent. So maybe the activity will help. We're basically going to use this generated data set to apply all these different tuning techniques we just talked about. So you'll want to just run this cell that will give you your X and your Y. So you have to basically set up your data, make sure everything's the right shape, make sure you look at the target, and then decide on your model architecture. So how many layers you're going to start off with, what your optimization or your optimizer is going to be, your activation functions, and then what your output's going to look like. So train a baseline model and then look at your results. And depending on those, you can kind of go back and implement some of these things and try to basically improve its performance. So that's the activity. We have how many people? Let's see. Okay. I guess I'll just pick someone then. Let's see. I'll have Brendan explain if you want to.
Sure. So I am actually running a new model as well, but I'll go ahead and share mine. All right. So obviously here we can tell is that we've got 1,000 features, 10,000 samples, 5 classes that it can be categorized as. So the first thing we did is we one-hot encoded our Y, did a train test split, test size of 0.2. We're just looking here to validate that the Y got transformed properly with the one-hot encoding. And so here is where we've tried, I don't know how many different configurations of this thing. Obviously, the first problem that we identified immediately is that it gets overfit very badly, very quickly. If you just kind of ran a preliminary model and got a train accuracy of 0.96, your test accuracy was terrible. So as we went along, we kind of started adding some more layers, tried a Gaussian noise layer as well, changed the learning rate, did a optimizer with a lower learning rate, a couple of things as well. Obviously, because we've got 5 categories, our activation layer has 5 neurons with the softmax activation function, changed the loss function to categorical cross entropy, and have just been experimenting with different batch sizes, epochs, early stopping, just trying to get the overfitting to come down. And this is close to what we had for our best. You can see here that we were starting to tail off early, so maybe lower the patience a bit so it kind of stops there. We still never really got it to a great spot. The last couple runs ago was the best one that we had, which was about a 0.85 train and a 0.5 test. We tried something else. That didn't work. We tried adding another noise layer. It got worse. So we went back to this one. And you can see here that the results are close-ish. Not quite as good as what we had on the last time, which was our best run, but close-ish. Yeah, so we've been trying to play around with all different settings, had different neurons in all of our dense layers. But this is so far the closest we've gotten. If somebody else did better, I would be really interested to see it because we've been struggling hard.
I think Beth, Bonnie, and Anubhav, you guys got a better score than that, right?
Yeah, Anubhav has over 60.
Yeah.
Do you want to show yours?
I didn't really do much. I mean,
Could you hold your mic a little closer? It's kind of quiet.
sorry. I didn't really do much. I just added a noise layer and a dropout layer over here. Bonnie pointed out that having less hidden layers improved accuracy. And I ended up with, I'm pretty sure just overfitted, but still 66% test accuracy.
That's pretty good.
Yeah, if you looked in this one before, this was without the noise. It was at 65.5%. So noise helped it by 1%, 0.5%, I guess.
So
Cool.
Matt, one thing that stands out that's the major difference between theirs and ours is their dense layers had way fewer neurons than ours.
Yeah, that could be something.
Actually, I did one that had over 500, and I'm still getting rather over 60%.
I give up.
So that's the thing, though. It's random data, right?
Right.
And so we're literally trying to find meaning where there isn't any. And so that's why Dropout was so effective, is because that's what Dropout does, is it removes those false nodes. It removes things that are overly weighted whenever they're not supposed to be. And so Dropout was always going to work the best out of any of these tuning parameters that we have, because our model was generated using random data. And I think that's probably why, Matt, you put in this homework to do a neural network on our Mod 5 data set, because that will actually show us what these tuning parameters do. It's really hard to train something on random data. Adding noise helps a little bit, but again, you're adding noise to what's already random data, which is just noise itself. The regulation stuff, that's not going to be really, the regularization stuff isn't going to be really effective either, because we don't need to do a lasso or a ridge, because we don't have anything that's really outstanding.
Yeah, no, that's great. I think you are spot on there. I wanted to give you guys something difficult. It is going to be really hard to fit an accurate model to this data. I think 60% around there is going to be about the highest you'll get on the test. But you still will run into this issue a lot with the overfitting. So that's kind of I wanted to highlight. And Beth's right, like dropout in this case is going to be the best thing. In my example that I did, I added a dropout actually after each dense layer, and that had good results. I also told some of you to shoot for a dropout of like 0.1 to 0.05. I actually increased it to like 0.25, and that made a difference. That won't always be the case, but at least on this data set. And yeah, and neural networks are kind of meant to fit to, you know, stuff that happens in nature where there's actually underlying patterns that humans can't really recognize, but a machine can. So it does make sense that they won't perform the best on random data. And that is why your final part on this notebook is to take your mod 5 data set. You have it all set up, your X and your Y. You might have to manipulate the shape of it a little bit, but build a neural network using the stuff we learned and see if you can match the accuracy you got or even outperform it. I think that would be a really good exercise. And then using real world data. So does anyone have any questions before we go here tonight? I know this is a lot. That's why we have like 3 or 4 study groups on one topic, because it is a lot. You kind of just have to get experience with it, and then it starts making sense.
Yeah, it's actually, I think this part is okay because basically you just change all the parameters. But there was one lab that used a linear algebra that I struggled with.
Yeah, the actual math for all this is really complicated. I would recommend some YouTube videos for that. That 3 blue, 1 brown, or whatever.
Yeah, I
I'm sure you
checked
can find
over
it.
the weekend. But the way he explained is simplified. But actually the labs, I think I don't know if you guys did that, but I failed. Like, yeah, I need some help.
So I've read in a couple of places that the Learn curriculum is designed to where you get to the lab, it's really hard, you have to click on done and look at the solution, and that's where your learning takes place. So if that's what you had to do, Bonnie, don't feel bad. A lot of people do that.
Yeah, I did check the the solution, but I still like want some help understanding the cost functions and like, yeah, it might be helpful to go back to more mod 3 or like mod 4 to check the linear algebra portion.
Yeah, and all the gradient descent stuff.
Yeah.
I did find this one video. Let me post it here. It's like over an hour long on the math behind neural networks. That's probably a good one.
But for the later sections, do we need to know all that?
I don't think so. I think everything else is just going to be more practical.
Okay,
Because we're
okay.
going to do convolutional neural networks Wednesday, but you're not really going to get too deep into the math on that, because that's starting to get like out of the scope of what we
Okay.
really have time for. But yeah, so there's a little bit with the convolutional neural networks, but then after that, we do transfer learning. There's no math there. Deep NLP, there's not really any math there. Yeah. Yeah, as long as you understand like kind of the basics of how to calculate everything in a neural network, then you should be fine.
And understand too, Bonnie, like this is the limitation of math. Where we're at in the curriculum right now is literally the end of math knowledge. So anything that comes after it is going to be something that people create today. The stuff that we're learning was created less than 10 years ago. So if it's really hard, that's because it's at the end of our knowledge.
Yeah,
Yeah,
I
that's
agree.
a really good point.
Yeah, I have to trace back to 10 years before. If I learned this stuff 10 years ago, maybe better.
Like the people who understand this math really well basically have a PhD in it. It's
Really?
like getting to
Yes.
that level. Mm-hmm.
Yeah, this is graduate level math, and it's beyond a master's.
Yeah, because I remember when we do the gradient descent and the cost functions is they didn't go that deeper, like go that deep to understand the stuff that we are learning now.
Yep. Yeah, all the matrix math too. It's a lot.
Okay, thank you guys. You made me feel
Yep.
better.
Yeah, no, don't worry.
And I highly recommend the the three blue, one brown. They're
Mm-hmm.
genius.
He's
So
phenomenal.
yeah.
Yep. Alrighty. Well, thanks for coming out, everyone. I'll
Thank
see you guys on Wednesday. We're going to be doing some fun stuff with computer vision. So be
Okay.
excited for that.
Woo.
All right. Take care, everyone. Bye.
But